Formation control rests on one assumption, a initial rigid communication graph. But in practice, agents sense only within a limited range, so this rigidity rarely exists at the start. We begin with what the robots actually can sense, a time-varying communication graph. Minimal rigidity in two-dimension needs at least two n-3 edges to be acquired. Our novel contribution is a deadlock-free CBFQP framework in which each follower acquires its missing edge under a collision-free consensus protocol, forming a minimally rigid consensus graph, and guaranteeing rigidity for heterogeneous, nonlinear multi-robot systems. We start with the time-varying communication graph, where an edge exists only when a neighbor lies within an agent's sensing range. From this graph, we extract a time-invariant subgraph, a layered, leader-rooted spanning forest, constructed by interleaved breadth-first indexing and recursive directed star expansion, which forms the interleaved layered directed acyclic graph, or ILDAG. The multi-agent system is deployed across two settings: physical robots in a motion capture arena alongside some agents in gazebo simulation. Agent 3 and 9 illustrate the time-varying communication graph showing every edge within their sensing range. Then we show the time-invariant ILDAG subgraph by traversing each leader-rooted tree, layer by layer. With the previously formed subgraph, a consensus-driven CBFQP framework drives the agents into the splay scheme, a structured spacing that ensures inter-agent safety while bringing the required rigidity edges within the sensing range of each layer. As shown for agents 3 and 9, the second parent required for rigidity lies outside their sensing range. As the splay scheme forms, its layered orbit decay brings that edge within range of each layer, ready to be acquired. Each agent runs a hierarchical second-order formation consensus, agreeing on position and velocity with its parent across layers. The splay configuration is collision-free by construction. Each layer's orbit shrinks geometrically, holding every agent beyond the safety radius. So the scheme scales to any number of agents. Additionally, a collision cone control barrier function, solved as a quadratic program, steers each agent's relative velocity outside the collision cone. Most importantly, the scheme is deadlock-free. The classic failure in rigidity and safety is deadlock. Competing objectives leave agents stalled, chasing rigidity while halting for safety. The splay scheme eliminates this. Every agent is assigned a distinct target on its orbit, keeping a clear, collision-free path toward rigidity. The key novelty here is this control acts only on the time-invariant subgraph, yet indirectly reshapes the time-varying edges. Rigidity emerges without being controlled directly. As you can see, the agents converge to the splay scheme, driving position and velocity errors to zero. Now, following the Henneberg sequence, each follower keeps its intrafamily edge to its tree parent and acquires one cross-family link to a second parent in a neighboring family. The link is cross-family by design, tying the families together so rigidity spans the whole graph, not a single tree. Which second parent it reaches is set by sibling rank. A follower connects to the next ranked parent in its own tree, while the last ranked child crosses into the adjacent tree. Each addition adds one edge, taking this example from 13 edges to 25. Exactly 2n-3, the minimal rigidity count. On the hardware as well, Agent 3 and 9 confirm the second parent now lies within their sensing range, completing the minimally rigid graph at 25 edges.